Next worksheet, maximum power transfer theorem. We've got a circuit up here that's very similar to the circuits that you've been using with Thevenin's and Norton's theorems. And before we go into that, though, I need to tell you what the maximum power transfer theorem says. Maximum power transfer theorem says that maximum power, I'm going to write this on the board, maximum power is delivered to a load when RL equals R source. Now the first thing we're going to do to our circuit over here is to convert it into a Thevenin equivalent circuit. And that will look, of course, like all Thevenin equivalent circuits look. We have a voltage source in series with a resistor. We'll call the resistor RTH and we'll call the voltage VTH. As you recall, VTH represents the voltage present at the open circuited output terminal, and RTH represents the resistance looking into the open circuit output terminals. By open circuit output terminals, we mean to remove the load. Now, if we say maximum power is the power delivered to a load when RL equals R source, or that's when maximum power is delivered, then the source resistance is equal to RTH. So when RTH equals the load resistance, whatever that is, when those two things are equal, that's when we will always be delivering maximum power to that load. That's why when you look at your amplifier system, for example, and it says use 8 ohm speakers, that means that the output impedance of your amplifier is 8 ohms. You put 8 ohm speakers on it, that means you deliver maximum power to those speakers. All right. Now, since you have already had instruction and plenty of practice and been tested on how to do how to come up with a Thevenin equivalent network, I'm not going to do that for you. I will, however, tell you what the values are that you should come up with. Let's go over these. R1, this is my source voltage here. V source is 55.33 volts. R1 is 5.81 K. R2 is 4.95 K. R3 is 7.13 K. R4 is 4.95 K. And R5 is 1.64 K. You might want to do a little bit of a close-up on that so that everybody has a chance to write that down. Give you just a minute to get those values down. While you're writing those values down, I am going to go ahead and tell you that for RTH, you should get 8.47 K ohms. And for VTH, you should get 4.3 volts. I'll give you just a minute to get caught up. All right, now then. Let's look at this a little bit with respect to some information that we know. We know that the voltage divider rule can be used to find the voltage across the load resistance. Well, if RL equals RTH, that means that the load resistance is also going to be equal to 8.47 K when we are delivering maximum power to the load, because that's what the maximum power transfer theorem says. Now then, what is the maximum power? In other words, what is the maximum power? Since RL equals RTH, I know that I will have 1/2 VTH across that load, since those two resistors are equal. Therefore, I can calculate my maximum power as 1/2 VTH squared divided by the value of RTH. Now then, in this case, that turns out to be 540, yes it does, 547 microwatts. 547 microwatts is the maximum power this circuit can deliver. And it will always deliver that amount of power when the load is equal to the source resistance. In this case, the source resistance again is RTH. Now, you have a little table down here on your worksheet. It says use the following load values to determine load power and to demonstrate the maximum power transfer theorem. Well, there's two things you have to do there. You have to put the first resistance load here, and that will be 847.43 ohms. Then you choose, this is RL table here. The first one is 847.43 ohms. The voltage delivered to that load, which obviously is not half of VTH, is 39 millivolts. The current is 462 microamps. Multiplying I times V, we get a power of 181 microwatts that is delivered to the load, PL, load power. If we continue that process, the next resistor is 4.24 k ohms. The voltage at the load is 1.44 volts. The current is 388 microamps, and the power is 487 microwatts. Continuing on, I'm going to now use an RL that is equal to RTH. 8.47 k ohms gives me exactly half the voltage that's applied, which is 2.15 volts. The current calculated through Ohm's law is 254 microamps. The power is 547 microwatts, and that agrees with our maximum power calculation we did earlier. We're going to continue increasing the load resistance, 16.95 K. You'll notice our voltage goes up 2.87 volts, but our current comes down now 169 microamps. And our load power comes down. Now it's 487. We've got one more, 42.37 K. Voltage is 3.59. Current is 85 microamps. Power delivered to the load is 304 microwatts. Now then, what is this telling us? This started out with a low value for the load resistance, something substantially less than the source resistance. We increased it, and as we increased it towards the Thevenin equivalent resistance, the source resistance, we saw that the power increased up to the maximum amount. If we increase the resistance of the load further, the power drops off. So that's the whole point of the maximum power transfer theorem worksheet, is to demonstrate to you that if we start out with a low resistance, much less than the Thevenin's resistance, go through the Thevenin's resistance, and then increase further on past that, we find that the power increases, is maximum when RL equals RTH, and falls off after that. So the graph of that down at the bottom of your worksheet would look something like this. You have R1, R2, R3, R4. I guess we had 5, didn't we? And you will find that it peaks out, and so your graph should look something like this, where the maximum power is delivered to the load when RL equals RTH. That's it.